who is Elena Redaelli.
Hi.
Yes, I
Shall
can
I share? Yeah.
Yes, if you can start sharing your screen, please.
Do you see annoying black bars or?
No, there are no black bars.
Perfect. Thank you.
Okay, good. Our next speaker will be Elena Redaelli, who will talk about the Hunt for High Mass Prestellar course. Please go ahead.
So yeah, first of all, thank you very much. I'm very happy of being here and listening to all this amazing science that I don't normally really work with. It also makes me feel much better about all my ALMA rejections, because indeed there is a lot of good, amazing science that you can do with ALMA. My main research focus is star formation, and today we'll talk a bit about high mass star formation in the galaxy, of course, so in the Milky Way. So I guess I don't have to convince you that high mass stars, despite being much rarer than low mass stars, are the ones that affect most deeply the dynamics and energetics of the interstellar medium. Despite their importance, though, the initial stages of high mass stars, so the, let's say, star formation of these objects, is significantly less known than the low mass counterpart. And from the theoretical point of view, there have been a couple of models developed, the main one being the so-called turbulent core accretion model, which is basically a scaled up of the process in the low mass regime. And then you have the competitive accretion model. What this theory mainly differ in, well, not mainly, but one of the things in which they differ is their predictions about the speed of high mass stars. So the main question here is, do high mass, so massive prestellar core truly exist? Or instead, the high mass stars form essentially low mass, and then they keep accreting mass during the protostellar stage. And answering this question from the observational point of view is quite tricky. It's quite tricky because high mass stars are rare, as you know, and so they are on average way more distant with respect to the low mass counterpart from the solar system. They are born usually in clustered environments, which are very crowded, very heavily obscured by dust. So a common strategy is to target so-called infrared dark clouds, which are cluster clouds, which are dark at infrared, so like 24 microns or 70 microns, which are believed to be the birthplace, the nurseries of high mass stars. But of course, you need interferometers here, because without something like ALMA, and especially thanks to ALMA, you would never have the resolution and sensitivity to really disentangle the crowded environment in which you hope to find progenitors of high mass stars. A second problem is what tracer to use to identify these high mass prestellar core. And this is challenging because on one hand, you can do continuum surveys with ALMA, Penfree, Penn6, whatever, where you can identify quite easily and without a long exposure times cores. The problem of continuum emission is that you never know whether those cores are truly prestellar or whether they are so bright, for instance, because there is a rise in temperature due to the fact that there is already a protostar inside. So recently, we developed, let's say, a tool where what we do is that we use HORT H2D+. Or H2D+ is a very unique tracer because it's a light deteriorated molecule. It does not suffer from depletion. And as soon as the temperature rises above basically 20 Kelvin, its abundance is significantly lowered because you start to have CO back into the gas phase due to the thermal desorption. And so detecting HORT H2D+ is a quite an ambiguous signature of having a prestellar phase object. So in 2021, we reported these two clump. These are two intermediate mass clump, let's say, which were observed in ALMA band 7 in cycle 6. And we reported the first actually interferometric observation of ortho-HD plus in such objects. And what we did is that we used a core finding algorithm known as CHIMES to identify prestellar cores in position velocity space in the ortho-HD plus cubes. And we found these cores, which are shown here with these green contours on top of the continuum emission. And the interesting thing is that none of them was more massive than tensor masses. The point is that these two sources are actually not essentially high mass in the sense that the clump masses are about a couple of hundreds of solar masses. So it's debatable whether they have the potential to form high mass stars. And so what we did next is that we targeted another clump. This is AG14. And this is a big boy. This is a more than 5,000 solar masses clump. So this is definitely have the capability to form high mass stars. We know already that AG14, despite being dark at 70 and 40 and 24 microns as observed with single dish, we know that it has been already active in star formation. So this clump was part of the ASHES project led by Francesca Mesa. And in this paper from me of a couple of years ago, they used ALMA band 6 data to investigate the protostellar outflows. And they found that at least 6 cores are associated with outflows seen in CO and FIO, which means that indeed there has been already some star formation going on in this clump. These are our band 7 data. The resolution is about 0.7 times 0.5 arc seconds. So in linear scale, we're talking about 1,500 to 12,000 AUs. We observed it with the main array and the ACA. Unfortunately, we don't have total power data, but Francesca yesterday told us that it would have been very important to have it, but unfortunately we don't. And the spectral resolution is about 20.2 kilometers per second. Here you see the continuum emission color scale, the ortho-HD plus integrated intensity in contours, and the protostellar candidate with these green stars. And as you can see, basically most of the detected protostellar candidates are associated with peaks in the continuum emissions. However, not all of them are associated with bright ortho-HD plus emission, which suggests that these peaks in emission, in thermal emission, are actually due to rise in temperature because you have there already protostellar feedback. We use the same algorithm, CHIMES, that we used in 2021 to identify prestellar cores, and here you have them. Their contours are shown with white on top of the continuum emission. And again, you can see that basically the protostars are located either outside or at most at the edges of the identified cores, highlighting this feedback that basically makes ortho-HD plus undetectable when the temperature rises above 20 Kelvin. And we estimated the masses of these objects from the continuum emission at 0.8 millimeter. And I highlighted here the estimates at 10 Kelvin. As you can see, we have 4 cores more massive than 10 solar masses, but none of them is more massive than 30. The point here is that the crucial parameter is the dust temperature. Of course, we have only one ALMA band, so we cannot say something about the dust temperature, while it would be crucial to know reliably the temperature in order to give proper mass estimates. And for that, we have actually submitted a BLA proposal to detect ammonia, which is a reliable thermometer of the prestellar gas. And we hope that this could help us really disentangle whether there are very massive cores in here or not. And finally, we also have Penfree data. So AG14 was covered in Penfree at the frequencies covering the N2H plus 1 to 0 line at 93 gigahertz. And here you see the cores identified on top of the integrated intensity of this line. Actually, I will focus here on only the hyperfine isolated component. So if you're not familiar, N2H plus has a very rich hyperfine pattern because it has 2 49 atoms, but it has a single component which is far away from the rest. It's actually a triple component, but it's the degenerate. And so you can assume that that is a pure Gaussian, let's say. And I will focus on that. The N2H plus emission shows a very complex kinematics, actually. You can see that basically everywhere in the source you have at least 3 velocity components, which are usually 0.5 kilometer per second to 1 kilometer per second apart. So what I did is that I fitted this data using free Gaussian component analysis in PySpec Python. And the idea of this bit of the project was to use this transition really to investigate the kinematics of the clump. Not really in the core, because these Penfree data are at much lower resolution than the Pen7 data. But we want to say something about the kinematic of the gas in which the cores are embedded, to start to looking for this core clump, let's say, transition, and to see what happens kinematically there. And here you have, for all the detected cores at their brightest pixel, you have a comparison of the ORTH2 plus data, which are shown in black. Then you have in blue the N2H plus data, and in red is the best fit to the N2H plus 1-to-0 transition. And first of all, the best fit is quite good. Second of all, you can see that all the time when you have ORTH2 plus line, you also have an N2H plus component. This means that we really can target that component in order to say something about the gas, the kinematic of the gas associated with the formation of that single core. And this is what we try to do. So here what I'm showing is a velocity position plot, a PV plot, basically, a reverse PV plot. So you have right ascension offset with respect to the center in x-axis, and the y-axis is the centroid velocity of each Gaussian component that have been fitted to the N2H plus line. So I have 3 components, so you have red, blue, and green. Then you have the position of the cores shown with these black circles, and then the position of the protostar shown with the magenta triangles. And what you can see here is that basically all these 3 components of velocity components are associated with both prestellar cores and protostellar candidates, meaning that indeed they all have been active in star formation. So there is not a main velocity component and the other 2 are just overlapping on the line of sight. Second of all, the blue and red component seems to have a morphology of sheets. So they are not filamentary like structure, they are more sheets and more or less constant velocity. But interestingly, we detected this feature here. This is a sort of filamentally like structure, and you can see it also actually in 3D, which extend as a velocity gradient of about 8 kilometers per second per parsec. And you can see it extends between 2 protostellar objects, and it is associated with at least 4 cores. And if we go and look where it is in this plot, yeah, thank you. It's here. So these are the 2 protostellar candidates that I was talking about. And here we zoom in. So what you see here is the background color scale is the centroid velocity of the Gaussian component, while in blue and red you have the blue shift and the red shift outflow emission. And as you can see, this filament which extends here seems to overlap with these red low, but actually its velocity is not consistent with it. So its velocity is actually blue shifted with respect to the local standard rest velocity of the protostar here. So this is pure speculation by now. It's work that I am currently doing. What we think we're seeing is actually we're seeing material within the N2H plus material flowing toward the protostar, and then material being ejected from the protostar with the outflow. And the two structures are actually likely perpendicular, but they happen to be in projection overlapping on the line of sight. So with this, I think I'm done with my talk, but so here it's really, it's a difficult source because it's extremely rich of outflows and flows of gas and so on. And we have actually a lot of data, which sometimes does not make things easier, it makes them only more complicated. But with this set of ALMA data, we could really say something, I think, about the prestellar population in this object and about their accretion properties. And this is what I'm trying to do. And so I'm early, but I will gladly take questions, if any, or discuss anything that you would suggest.
Thank you very much for this very nice talk. Well, indeed, more data is just more questions and makes things complicated. Alvaro?
Yeah, so I have some questions, but I start with one that it's in the chat. So they were asking if the ALMA band 3 data, if it was also 12-meter array plus 7-meter array. So it's
no, there we have also total power, like luckily. So yeah, because otherwise it would be a mess, because it's so extended and to each plus emission that without total power you would filter out a lot of emission. Already in RH2D plus, the point is that when the data were asked, I think that they were not, I was not in the proposal, but they were not expecting such extended emission. And that's why total power didn't seem necessary. But actually you see RH2 plus basically everywhere. And that would make total power a nice add.
So if there is more time for questions, so I have several. If there is no time, I will write them in Slack. But there is another one that it's, could you explain the filament versus sheet comparison a bit further? Were the Gaussian components grouped together based on velocity coherence? For example, using something like a friends of friends algorithm?
Okay, so no. Let's answer the second question. No, I did not use something like SCALs or something like friend of two friend algorithm. The reason being is that I never did it, and so it's something that we have thought about actually. The point is that at least some of the components, sorry, I'm trying to, my keynote is crazy. At least two components have very well distinguishing velocity. So I think that there is no ambiguity saying that these are two components, two individual separate components. Then here things become way more complex. The morphology of sheets, what I'm saying is that if you look in 3D plots, you don't see like these nice filaments that overlap, but what you see is basically really gas everywhere. Actually, to produce this plot, I have to make a very harsh cutting signal to noise ratio, because otherwise you have NH plus everywhere, and so you don't understand nothing of what you're seeing. But basically, it's not like you have overlapping filaments that have the aspect of filament in Ryan Deck. Did simply overlap. You more have like a very broad distribution of gas in Ryan Deck, which appear quite coherent in velocity. And so this is why I'm using the term sheets more than filaments, with the exception of this thing here, which instead really looked like a filament, honestly.
Okay. Thank you. So if there is time for some more question.
Yeah, we have time for one more question. Okay,
then while people think about, I will ask one of the many that I have. So in this plot that you have here, so we can see some velocity gradients and so on. Have you explored if there are like signatures of mass inflow or mass accretions or mass transport from this more diffuse gas into the positions where you have identified this starless core? So could you say something, or it's too messy?
So I try. So my naive idea was, okay, so now we have its velocity component, and you can zoom in around the core and say something about where the gas is flowing. The short answer is that it's too messy, and also, I mean, another thing that I haven't done is estimate, like, for instance, in this object here, it would be quite easy, I think, to estimate mass inflow rate. The point is that I don't have the continuum. So so what do you use for mass? So this is, but I think it's possible, it's feasible, and and I think that we have somewhere 3 millimeter continuum, so we should be able to say something on that. But on the individual core, it's simply too messy.
Okay, thanks.
Okay, thank you, Alvaro. You can type your other questions on the Slack channel. Thank you, Elena, again for the nice talk. Then